Okay, so in this lesson we are going to talk about how we graph sine and cosine functions. So knowing the parent function and then using our knowledge of vertical stretches, compressions, horizontal stretches, and compressions to create the graph of a transformed sine or cosine function. So what we're going to do here is look at, here's our parent function here. So we've learned about stretches and compressions for both vertical and horizontal. So here's our parent function. Looking at this graph right here, what we notice is that the zeros are in exactly the same positions as they are in the parent function, which means that no horizontal stretch or compression has taken place. We notice, however, that the maximum values here of 2 are now at 6. So this is representing a vertical stretch. Here we notice that the zeros have changed. So the zeros of 4 and 8 now occur at 2 and 4, which are half the distance to the origin or y-axis as they are in the parent function, which means we have a horizontal compression. In this one, we notice that the zeros are now at, the first zero is at 8 instead of at 4, so it's twice as far away from the origin or the y-axis. So that's a horizontal stretch. And in this one, what we notice, the zeros again are exactly the same places, 4 and 8, but the maximum values of 2 are now at a maximum value of 1, which means we have a vertical compression. So these types of transformations take place in the graphs of sine and cosine functions. First thing, though, that we are going to want to do is basically learn that we are looking at the points of the unit circle. We need to make sure that we understand, here's our function here, of f of theta equals sine theta. This is our parent function. And we're looking at these 5 points for a specific reason we'll talk about in a moment, over our interval from 0 to 2 pi, what the corresponding sine values would be for these angles in radians. So at 0 radians, we know that our sine value would be 0, the y-coordinate. At pi over 2, we know our sine value is 1. At pi radians, we know our sine value is again 0. At 3 pi over 2 radians, we know our sine value is negative 1. And at 2 pi radians, our sine value is again at 0. These 5 points are basically the main ones that we use to graph transformations of sine functions. Over the interval from 0 to 2 pi, the points that are the x-intercepts are the points that correspond to where we have 0 values. So 0, 0, pi 0, and 2 pi 0 are all x-intercepts. They would occur as points on the x-axis, or theta axis if our variable is theta. Over the interval from 0 to 2 pi, the relative maximum here would be pi halves comma 1, which has the largest y value. And over this same interval, the relative minimum would be 3 pi halves comma, or 3 pi halves comma negative 1, yes, because that negative 1 is the smallest sine value. And so that, those points, knowing these are your intercepts, or zeros, maximum and minimum occur at those 2 values, allows us then to generally, once we get comfortable with that, quickly and easily graph sine functions. So that's what we're going to do right here. We're going to focus on graphing our parent function. So we're going to use the points that we have on the previous one. We're also going to look at using some others here. So we know that sine of 0 is 0. We've learned that sine of pi 6, which is our 30 degrees, would be 1/2. Pi over 2, the sine is 1. At 5 pi 6, what we're looking at is a sine again of 1/2. At pi, our sine is 0. 7 pi 6, our sine is negative 1/2. 3 pi halves, sine is negative 1. 11 pi 6, we know sine is also negative 1. And at 2 pi, we're back to having a sine of 0. So these right here are the primary ones that we tend to graph, but I want to throw in the 1/2 so you can see the full shape of the curve. So we have 0, 0. We have pi halves comma 1. We have pi comma 0. We have 3 pi halves comma negative 1. And we have 2 pi comma 0. At pi 6 radians, which is roughly right around in here, we're at 1/2. At 5 pi 6, which is roughly right around in here, we're at 1/2. At 7 pi 6, which is roughly around in there, we're at negative 1/2. And at 11 pi 6, which is roughly around in here, we are also at negative 1/2. So the sine curve over this interval, this is actually what we call one period of the function. We call this a wave curve. And those of you who have taken physics might remember learning about waves a little bit. Sine and cosine are often the models, the mathematical models for things in physics that move in wave patterns. So this would be our parent function. F of theta equals sine theta. And so knowing this, especially these 5 points, is what's going to allow us to quickly and easily graph some sine functions. There it is from the graphing calculator. Here what we're going to look at doing is, so most often we have to graph sine and cosine over more than a single period. So coterminal angles differ by a multiple of 2 pi. So what this means is that as we move through that first 2 pi with our points, that same pattern actually repeats in the next interval of 2 pi, both to the right and the left of the first interval. So we are going to use this fact to extend the graph of f of theta equals sine theta to the left and right by one cycle. So we'll start with what we just graphed. So we know we have 0, 0, and then at pi halves our sine is 1. At pi our sine is 0. 3 pi halves our sine is 1, negative 1 rather, and at 2 pi our sine is 0. So now that pattern is going to continue. So from here, at the next half pi interval, we are going to be back at positive 1. And then we're going to be back at 0. And then we're at 7 pi halves, we will be at negative 1. And then at 4 pi, we will again be at 0. So we have this same wave function. So we have this piece here. That's our first wave. And then it repeats. Here's our second wave. And then the same thing happens to the left. So from here it's heading down. So at negative pi halves it would be at negative 1. At negative pi would be at 0. At negative 3 pi halves sine would be 1. And at negative 2 pi sine would again be 0. And it continues waving now in that. There's a third wave to the left. So now, and this is what we call periodic, meaning that the graph repeats itself over a consistent interval, in this case 2 pi. Alright, so now what we're going to do is look at doing something similar but for our cosine curve. So now we're looking at f of theta equals cosine theta. We're going to complete the table and then we'll draw a smooth curve to graph the parent function for the cosine family. And we're going to do this over this particular interval. But we're going to start with 0 to 2 pi. So what we know about the cosine at 0 radians is that the cosine is 1. And again, these are going to be the values and angles that we're going to want. These are going to give, so I'm going to skip over the every other one right now. At pi halves, we know cosine is 0. At pi, cosine is negative 1. At 3 pi halves, cosine is 0. And at 2 pi, cosine is back to being 1. At pi thirds, which is our 60 degrees, our cosine is a half. So at 2 pi thirds, where cosine is negative, this would be negative 1/2. 4 pi thirds, the third quadrant, cosine is negative, so negative 1/2. 5 pi thirds, fourth quadrant, cosine is positive, so positive 1/2. So graphing, and I'm just going to graph the key ones that give us both maximums, minimums, and intercepts here for this purpose. So I have, 0, 1 is where I start for cosine. Pi halves cosine is 0. Pi cosine is negative 1. 3 pi halves cosine is 0. And 2 pi cosine is 1. So this is actually a full wave, but it's in a different piece from sine. So this is the maximum, so this is what it looks like. So it's coming down, and then this is like a trough area of the wave, and then it's moving back up to its high point there. So that extends to the left and the right in the same pattern. So from its maximum here at 1, at the next half radians, which 5 pi over 2, cosine would be 0. At 3 pi, cosine would go down to -1. At 7 pi halves, cosine would come back up to 0. At 4 pi, it would reach its maximum again at 1. And so we complete this wave here, and it moves down, moves back up, like so. To the left, same thing. So from this maximum of 1, at negative pi halves, cosine would be 0. At negative pi, cosine would be -1. At negative 3 pi halves, cosine would be 0. And at negative 2 pi, cosine would again be back at 1. So we get this wave completing here. And again, we could continue on because it's going to arc down after that and arc down after that, like so, towards the next 0 value. So, periodic function. Periodic function is a function that repeats its output values, its y values, in this case its sine or cosine values, at regular intervals called cycles. The length of one cycle we call the period of the function. So for sine and cosine, they both have a period of 2 pi radians. And we can change that period by stretching horizontally or compressing horizontally. So here we're looking at a period of 2 pi, where we have, this is a sine function, so we're looking at one full wave, up and down for the sine function between 0 and 2 pi radians. Here we have a horizontal stretch, and we're stretching this now, so here's where our wave starts, and here's where our wave ends at 4 pi. So this is a stretch by a factor of 2, because the period of 2 pi here has been lengthened to a period of 4 pi. And then here we're actually looking at, now we have the period, so here's our full wave right here, and it goes from 0 to pi radians. So it's half of the 2 pi. So that actually is a horizontal compression by a factor of a half. So it's taking it and squishing that full wave into a distance or interval of pi radians. All right, so we can change the period of the sine or cosine function, and two other things we want to make sure we understand are the amplitude and the midline. So the amplitude is like your maximum minimum. So the amplitude is the absolute value of the distance between the midline, which is where all the zeros here are, and this. So it's half the distance between the maximums and the minimums, actually. So from 1 to -1, that distance is 2 units. Half that distance would be 1. So it's an amplitude of 1. The midline is the horizontal line that goes through that middle place, which in this case is y equals 0. In this case, we still have a midline of y equals 0, but from 3 to -3, that's a distance of 6 units. So now the amplitude is half of 6, which is 3. And here, we're going from 5 down to negative, or positive 1 actually. So from 1 to 5, that's a distance of 4 units. And half the distance of 4 would be 2. So we'd have an amplitude of 2. And halfway between, so 2 units from the maximum and the minimum is right here. So we actually have a midline here of y equals 3. And at this point, we're going to talk about this portion of the lesson in part 2. So you can end this video and switch over to part 2, and we'll talk about this and look at our examples.